Roger Penrose says the double slit experiment is the only real problem that needs to be solved, because we don't know where the particle is going to appear on the screen, only the probability. So I have to interpret the relativistic slide rule. So here I've made B 0.4, and I've got my Y on 2. You can change it to 1 or to 0, and put it back to 2, say. Now notice this is the normal way of figuring it out with the probability wave. So there's the probability wave, and in the near field it doesn't look quite right, but in the far field it turns out to be correct. So there's the particle heading off on the trajectory, and it's going to arrive on the second fringe in this case. And I just change Y, and it'll arrive on the first fringe, the 0 fringe, or I can take it out to, in this case, there's a fourth fringe. There's no fifth fringe. There's a fourth fringe, a third fringe, a second fringe, first, etc. and 0. So, and it depends on this. That can change. And when we get to the speed of light, you've only really got a fringe at 0 and at 30 degrees, and the next one is gone. Let's take it back to about 0.4. Let's get rid of the probability wave, because I don't really need it. Instead, I'm saying that the particle makes quantum leaps, just like energy levels. And you can see here I've got my T function, and these quantized blue circles go from 0.5 to 1 to 1.5 to 2, and they cross, where they cross the T function, particle is allowed. So in this case it's allowed on that intersection of the red T function with the blue quantum level, let's call it, or whatever. But the particle can only jump, so it can go to be on the second fringe, or it can quantum leap to the third fringe, or it can quantum leap to the fourth fringe, and in this case there will be no fifth fringe. And notice that the phase waves, electromagnetic waves, they also work. They give the right result in the far field. It's exactly the same result as the probability wave, even though the circles are wavelengths and they're smaller.